Hello everyone, I'm Paul and today we're solving problem 440, kth smallest in lexicographical order. This is hard and here I will show you the intuition, approach and efficient solution. We're given two integers n and k and we need to return the kth lexicographically smallest integer in the range from 1 to n. Now in case you don't know what lexicographically smallest means, let's say we have these numbers and we want to sort these in lexicographical order. First, we'll transform each of these into a string, and then we need to compare these numbers. So for example, let's say we compare 20 and 3. Here we will follow always the same process. We'll iterate every digit from left to right, and at each index we are comparing the digits in both numbers, and we are checking which one is smaller. So in this case we are comparing 2 and 3. 2 is smaller, so 20 is lexicographically smaller than 3. Now let's say we are trying to compare 20 and 200. Now we are following the same process. We iterate this from left to right, and at each step we are comparing the digits in both numbers. So first we compare 2 and 2, these are equal. Next we have 0 and 0, these are equal. And next we have a 0 down here and an empty space here. So in this case, the lexicographically smaller string is 20. So 20 is lexicographically smaller than 200. So with this in mind, if we were trying to sort this in lexicographical order, it would stay as it is. We will have 20, 200 and 3. Now going back to the problem, let's say we have n equals 13 and k equals 2. In this case, the lexicographical order for n is this. So the second smallest number in this array is 10. K is 2. So we take the second smallest number and we return 10. Now you might think about solving this with DFS, and more specifically with pre-order traversal DFS. But the problem is here. N is smaller or equal to 10 to the power of 9, and the DFS approach runs in big O of n time complexity, but given this constraint, we need to think about something more efficient. So here I will show you how can we solve this. Let's say n is 13 and k is 6. With this we can build this tree, and in this tree we have 0 digits for level 0, 1 digit for every number in level 1 and 2 digits for every number at level 2. And here we will try to simulate a pre-order traversal DFS without doing the DFS. So let's see what pre-order traversal DFS is. We start from the root and we go in this direction, and each time we visit the nodes from the left. So we start from the root, we go here, we visit 1, then we continue, we visit 10, we continue, we visit 11, then we visit 12, then we visit 13, then we visit 2, then 3, and so on. So if we run this DFS here, we iterate these numbers in lexicographical order, which is what we want. But remember, that requires a time complexity of big O of n, but n can be up to 10 to the power of 9, so we need to think about something more efficient. So we'll start from number 1, and first we will try to jump to this branch, to the branch with 2. And if this is in bounds, we will subtract from k the number of steps required to jump from 1 to 2. Now comes the tricky part. We need to count the amount of steps to go from node 1 to node 2. And to go from node 1 to node 2, we need to go through all of these nodes. So we need to compare this tree with this tree. And we are doing this level by level. So first we start here and we take the amount of steps from 2 to 1. So up to this moment we require 1 step. And now we go to this node. And the way to go to this node is we take each of these nodes and we multiply them by 10. So 1 times 10 is 10, and 2 times 10 is 20. So for the moment, let's say we have a 20 below 2, and our goal here is to add these many steps here. So we can take the minimum between this node and n plus 1, because n is included, and subtract the node for the tree in the left, meaning 10. So in this case, the minimum between 20 and 14 is 14. So 14 minus 10 is 4. So we add a 4 here. So we require 5 steps to go from 1 to 2. And these trees might have more levels. So for example, below 10 we could have 100, and we will do the same. But here, for example, if we have 100, 100 is out of bounds because n is 13. So now we know we have 5 steps from 1 to 2, and 2 is in bounds. We can subtract from k the amount of steps. So k is now 1. And given that we are trying to find the kth lexicographically smallest integer, we can subtract 1 from here to transform this into an index. So now we have 0 k's, and this means we can return the current number. Now we are at 2. We were at 1, and now we are at 2. From 1 we moved 1, 2, 3, 4, 5 steps. We reach 2, so we return 2. So this is the entire approach. Basically, we are trying to move first to the next branch and then to the next level. And we repeat the same process again and again until k is 0, and then we return the node we are standing at. For the time complexity, both of these operations require big O of log n time complexity. So overall time complexity will be roughly big O of log n squared. And space complexity will be big O of 1. So now let's go with the code, and hopefully you will get the idea. We start from number 1, so current is initially 1, and we'll work with indices from 0. So we subtract 1 from k. And now we'll create our function. We'll call this get steps, and this will take 2 values: the value for the first branch, for the branch in the left, and the value for the second branch. And here initially a count will be 0, and we will return this count. And in between, while branch 1 is smaller or equal to n, meaning if the value for branch 1 is in bounds, we add to the count the difference between branch 2 and branch 1. And now we need to update both branches to the next level. So branch 1 times equal 10 and branch 2 times equal 10. But we are missing something here. If b2 is out of bounds, we need to take n plus 1 instead. So here we can say if b2 is smaller or equal to n plus 1, then we do this. Else count plus equal n plus 1 minus branch 1. So with this function we can continue to the next part. Now while k is greater than 0, we need to take the amount of steps from current up to current plus 1, meaning the amount of steps to reach to the next branch. So steps equals get steps from current to current plus 1. And if the amount of steps is smaller or equal to k, meaning we can move to the next branch, well, in this case we move to the next branch, so current plus equal 1, and we need to subtract from k the amount of steps, k minus equal steps. Else, meaning if our target is in the left tree, we need to move one level in the left tree. So in this case, current times equal 10, and we need to subtract 1 from k. So this will go on and on until we reach the goal. First we are trying to move to the right, then we are trying to move to the next level, and finally we return current. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.